Welcome to Discrete Mathematics. Today, we are diving into the fascinating world of Boolean algebras. This topic might sound abstract at first, but it is actually the invisible brain behind every computer, smartphone, and digital watch in the world. By the end of this lecture, you will understand how simple true and false statements can be combined to build complex logical rules. To understand where this comes from, imagine setting up a smart home lighting system. You want the hallway light to turn on only if it is dark outside and someone is walking in the hallway. Every condition has exactly two possibilities, true or false, on or off. In the 1800s, mathematician George Boole realized human logic could be turned into a strict mathematical game. Instead of calculating with numbers like 5 or 10, you calculate with just two states. This allows us to build complex rules out of very simple yes and no building blocks. Now that we understand the basic values, let us look at how we combine them. A Boolean algebra uses variables that hold one of two values, usually represented as 0 for false and 1 for true. Instead of standard addition and multiplication, we use three fundamental operations. The OR operation outputs true if at least one input is true. The AND operation outputs true only if both inputs are true. Finally, the NOT operation or complement simply flips a value from true to false or false to true. These form our logical rulebook. These operations follow strict rules, starting with the commutative law for OR. Conceptually, this law tells us that the order in which you check conditions does not matter at all. In this formula, x represents our first variable, y represents our second variable, and the plus sign represents the logical OR operation. If you say that you want an apple or a banana, it is exactly the same as saying you want a banana or an apple. Changing the order of the variables does not change the physical outcome of the logical statement. Similarly, we have the commutative law for the AND operation. This formula shows that order is also irrelevant when requiring two things to be true simultaneously. Here, the dot symbol represents the logical AND operation. If you are checking multiple requirements, the sequence of your checks does not change the final outcome. For example, saying it is raining and it is cold means the exact same thing as saying it is cold and it is raining. Whether x or y comes first, both must be true for the result to be true. Moving beyond simple order, let us see how these operations interact with the distributive law for OR over AND. In regular math, addition does not distribute over multiplication, but in Boolean algebra, it absolutely does. This formula shows that if you have a condition x that is odd with a grouped condition y and z, you can distribute the x to both y and z individually. The variable z simply represents a third Boolean condition. Physically, this means a shared alternative condition can be applied separately to each part of a strict requirement. Just as OR distributes over AND, we have a second distributive law, which looks much more like the algebra you learnt in high school. This law states that if you require condition x to be true and you require either y or z to be true, you can multiply the x through the parentheses. It is logically equivalent to saying I need x and y or I need x and z. This rule is incredibly useful for expanding complex logical statements into simpler, more manageable parts when designing digital circuits. Next, we introduce the concept of absolute states with the identity law for OR. Conceptually, this law explains what happens when you introduce a guaranteed false condition into an OR statement. In this formula, the symbol 0 represents the absolute false state, meaning a condition that is never met. If you have a condition x and you say x is true or false is true, the final result depends entirely on x. Adding a guaranteed false condition to an OR statement changes absolutely nothing about the final physical outcome. In the exact same way, we have the identity law for the AND operation. This law explains how a guaranteed true condition interacts with other variables. Here, the symbol 1 represents the absolute true state, meaning a condition that is always met. If you say x must be true and true must be true, the result again depends entirely on x. Multiplying by a guaranteed true condition does not change the truth value of your original variable. If x is true, the result is true. If x is false, the result is false. This brings us to a profound statement of logic, the complement law for OR. This formula states that either a statement is true or its exact opposite is true. The symbol x prime represents the exact opposite or complement of x. Because one of these two conditions must absolutely be true in any situation, the result of ORing them together is always 1, representing absolute truth. Physically, this means that if you cover all possible states of a variable, the combined logical condition will always be satisfied, no matter what happens. Conversely, we have the complement law for the AND operation. This formula states that it is physically and logically impossible for a statement and its exact opposite to be true at the exact same time. You cannot be both fully asleep and fully awake simultaneously. Therefore, multiplying a variable x by its complement x prime will always result in 0, representing absolute false. If one condition is true, the other is guaranteed to be false, meaning the strict AND requirement can never be met under any circumstances in the real world. Now that we have our fundamental axioms, let us use them to prove the idempotent law. In regular math, 5 plus 5 equals 10. But in Boolean algebra, we want to prove that x plus x simply equals x. This chunk of the proof sets up our initial expression. We start with x plus x and we use the identity law to multiply it by 1. This is a clever mathematical trick to give us more terms to work with. Then we use the complement law to replace that 1 with x plus x prime. This sets the stage for our next algebraic steps. Continuing with our proof, we now apply the distributive law in reverse, which is very similar to factoring in regular algebra. Notice that both groups inside the parentheses start with the exact same terms, which are the variable x and the plus sign. The distributive law allows us to factor out this common x, leaving us with x odd with the product of the remaining unique terms, which are x and x prime. Next, we focus our attention on that x times x prime part. The complement law for the AND operation tells us that a variable multiplied by its opposite is always 0. So we replace that entire block with 0. To wrap up this proof, we focus on the remaining terms in our equation. We are left with x plus 0. We use the identity law for the OR operation to finish the derivation. Adding 0 to any variable simply leaves us with that variable because 0 contributes absolutely nothing to an OR statement. We have successfully transformed x plus x into x, proving the idempotent law step by step. The intuition here is that repeating an identical condition in logic does not change the overall requirement. This final result shows exactly how logical addition behaves differently from numerical addition. Having proven the idempotent law, let us tackle another important proof, the boundedness law for the OR operation. This law states that x plus 1 equals 1. This means if you OR any variable with a guaranteed true statement, the result is always true. We start our mathematical manipulation with the expression x plus 1. Just like in the previous example, we use the identity law to multiply the entire expression by 1. This does not change the logical value at all. Then we take that 1 outside the parentheses and replace it with x plus x prime using the complement law. Moving forward with our expansion, we again apply the distributive law in reverse to simplify the expanded equation. Both sets of parentheses contain an x followed by a plus sign. We factor out this common x, which acts as our shared term. This leaves us with x added to the product of the remaining unique terms, which are x prime and 1. Now we look closely at the term x prime and 1 inside the parentheses. The identity law tells us that any variable ANDed with 1 remains completely unchanged. Therefore, x prime and 1 simply becomes x prime, setting up our final step. For our final step in this proof, we look at the simplified equation staring back at us, which is x plus x prime. We immediately recognize the complement law. A variable odd with its exact opposite always results in 1, representing absolute truth. We have successfully proven that x plus 1 equals 1 using only the basic rules. The intuition behind why this works is simple. In plain English, if one part of an OR statement is definitely true, the whole statement is definitely true, regardless of the state of the other variable. This concludes our derivation of the boundedness law. So we have proven these mathematical laws. But why do they matter in the real world? Boolean algebra is the absolute foundation of the modern digital world. Without it, computers, smartphones, and the internet simply would not exist. Every microchip contains billions of microscopic electronic switches, called transistors, which can only be in two states, conducting electricity or not conducting electricity. Engineers use Boolean algebra to design circuits that combine these ones and zeros to perform complex tasks. Furthermore, every time you use a search engine and type something like cats and dogs, not birds, you are directly writing a Boolean algebra equation. To make these abstract concepts more concrete, let us visualize them using Venn diagrams. These diagrams provide a visual way to understand how Boolean operations work using the concept of sets. In the first diagram on the left, the OR operation covers everything in both circles, showing that the result is true if either condition is met. The middle diagram shows the AND operation, where only the overlapping middle section is shaded, proving that both conditions must be true simultaneously. Finally, the diagram on the right illustrates the NOT operation, shading everything outside the original circle to represent the exact opposite state. To wrap up our lecture, let us review the key takeaways. First, Boolean algebra is a specialized mathematical system designed to handle logic using only two values, true and false. Second, it relies on three basic operations, which are AND, OR, and NOT, along with a strict set of axioms. Finally, this system proves that human reasoning can be calculated just like numbers. You have now covered the full foundation of Boolean logic, which is the first step to understanding how all digital technology processes information.